question. In this lesson, we shall look at this question 6 on work, energy, and power. And obviously in South Africa, the transportation of goods by trucks adds to the traffic problems on our roads. A 10,000 kilogram truck travels up a straight inclined road of length 23 meters, as can be seen at a constant speed of 20 kilometers per hour. The total work done by the engine of the truck to get there is 7 times 10 to the 5th power joules. The work done to overcome friction is 8,5 times 10 to the 4th power. Now, there are a couple of things that remain very, very important here. One, to calculate the height h reached by the truck at the top of the road. And to do that, as I indicated earlier, we actually look at the fact that work done by non-conservative forces is the change in potential energy plus the change in kinetic energy. Okay, there are many ways to do the question, but this is the easiest, I believe. Okay. Now, the work done by non-conservative forces would be work done by to overcome friction, but also the work done by the engine, because those are forces that are actually non-conservative forces. Right. So now you'll have to take note of the fact that at this point, what we know and what we're able to see is that the change in the potential energy is mg h final h initial plus half m v final squared v initial squared. So now, what is this? What are the non-conservative forces here? The non-conservative forces obviously would do the kind of work associated with the engine and also the friction. Right, so now we're able to see therefore that we have 7 times 10, which is the biggest work done, which is the 7 times 10 to the 5th power, is the largest one, minus the smaller one, which is 8,5 times 10 to the 4th power. And now it is equal to this here. Now, at this point, you're going to use your calculators. I'm sure you are very alert now. And you have 8,5 times 10 to the 4th power. And this is the mass, which is 10,000. Right? 10,000 multiplied by the 9.8 or 9,8 meters per second squared, which is the gravitational acceleration. The actual height final, this is going to sort of be the height final, and you have the height initial. So the height final is what the examiner wants. Okay, so in principle, obviously you can say the height final, let's just call it h, because that's what the examiner calls it, when the truck reaches the top of the incline. And then now you'd have the zero height at the base of this. 10,000. Okay. Now the velocity is already seen that the v final is v initial. It is 20 kilometers per hour. And now 20 kilometers per hour can be seen as what? Right, so 20 kilometers per hour can be seen as what must be converted to meters per second, the kind of unit we use. So, and that is 20 times 10 to the 3 is 20,000. And once again, you divide, because of the hours. In an hour, you have 3,600 seconds there. And therefore, if you divide, we got 5,5 meters per second. Or we can call it 5,6. Right, because it's 5,55, etc. So that becomes 5,56. So just 2 decimal places, it's enough. Okay, now pay particular attention to this and make sure that you're able to note and understand what is happening here. So the velocities are the same. So in principle, then here you have the final velocity, which will be 5,5 which is square, and the initial is gonna, which will be 5,56. Let's just put it that way. So you have 5,56, right? And you square that minus 5,56. You square that. Okay, so yeah, this is what you have. And then now, as a consequence, now these two are the same. So this is gonna go to 0. So the change in the kinetic energy is going to be 0 because the speed does not change. It's 20 kilometers per hour. Even when the truck reaches the top, is the same thing. But now here we're able to get the height h. So the height h, therefore it's 7 times 10 to the 5th power minus 8,5 times 10 to the 4th power. And you divide. Okay, let's do the division together. Let's do the division together. So you divide by what? You divide by exactly whatever you have on this side. So here you'll divide by the 10,000 mass multiplied by 9.8, and therefore you're able to get the height h. Okay, calculators, please. Secretary. Anyone who is who's in the position of a secretary to just to do the quick. Okay, I'm just doing it because I need to make sure that we write correct answers here. 7 times 10 to the 5th power. Numbers are done. Minus 8.5 times 10 to the 4th power. And then you divide by 10 times 9.8. Okay, your. Okay, so what are you able to get? Yo, 6,276 meters. Approximately the same as 6,28. 28 meters. So now obviously the height reached by the truck at the top of the road is 6,28 meters, so that the height is approximately 6,28 meters there. Where's the question? Who is confused? Who is wondering what is happening here? Who is saying, hey, what's happening here? I'm expecting the answer to be a billion, a trillion, a zillion, but now it's this. Where's the question? No question. No question. No question. In the absence of a question, we move on. We move on. Right. In the next point, we want to look at the next question. The instantaneous power delivered by the engine of the truck. Let us calculate the instantaneous power delivered by the engine of the truck. What formula are we going to use to find the instantaneous power delivered by the engine of the truck? How much power is the engine of the truck delivering? How much power? Now, for us to do 6.2, we need to first note that we need to be in a position to calculate, right? Because now we're told that the total work done by the engine of the truck to get there is this one. But now also we need to know the actual, we can use power. Power is force times average velocity. Okay, so if power is force times average velocity, work done, which is change in x cosine theta. Right. We know that the work done by the engine of the truck to get there, because we want to calculate the instantaneous power delivered by the engine of the truck. But how do you find that? Okay. We know very well that the work done by the engine of the truck is 7 times 10 to the 5th power. which is the force, 23 meters, cosine 0 degrees. So that you have 7 times 10 to the 5th power. You divide by 23. Okay, because now when the engine of the truck goes up here, we need to understand a couple of things, that the force by the engine of the truck is upwards. So this force is upwards, and also delta x is also upwards, in which case, therefore, the angle between them is 0 degrees. That is why this is 0 degrees. Right, so yeah, because the delta x and the force are in the same direction. The engine of the truck is pushing the truck up. That's why this is 0 degrees. But now also we know that the work done by the engine of the truck is 7 times 10 to the 5th power. All right, and then we divide these things here. And then if you use a calculator, you'll get exactly 3,04. And to check this one, right, so using a calculator, we're able to see that you have 7 times 10 to the 5th power, and you divide it by 23, and the result is actually 3, 0.04 043 times 10. Okay, so we have 1, 2, 3, 4 to the 4th power newtons. So we get therefore that this is the actual work done by the this is the force rather that the engine of the truck sort of exerts, and therefore now we're able to say the power, the instantaneous power delivered by the engine of the truck would therefore become force times sort of the average velocity. We have the velocity of the truck, that obviously the velocity of exactly 20 meters per second, or 20 kilometers per hour, and we can convert that. We converted it, so that here we get and say what is the actual force. It is 3,043 times 10 to the 4th power. That is the force there. And the velocity, we calculated it, but you can also do it step by step and then say it is actually the same as 20, and the kilometer is 1,000. Divide everything by 60 because there are 60 seconds in 1 hour. So that in the end, you multiply these things. Okay, what is the answer to this, guys? These things, okay? So now I'm going to use a calculator here. And if you use a calculator, what we are able to get is that it is 1,6 times 10 to the 5th power. Right, it is exactly this one, to the 5th power. And obviously now power is measured in watts. Okay, we can convert to kilowatts, but we need to just confirm that indeed this is correct. Let's just confirm that indeed this is correct. And indeed we made no mistake there. I'm trying to verify here as well. 3.043 times 10 to the 4th power times, okay, we have 20,000. You divide by 60 by 60. Yeah, it is 1.69. Just write it like that. Getting 1.69 approximately here. Okay, 1.69 times 10 raised to what? 1.69 times 10 to the 5th power watts, like this. Watts like that. Okay, yeah, so therefore this becomes sort of the answer. This becomes the answer. Right, so. And that is the instantaneous power delivered by the engine of the truck. But yeah, you can write it in many ways. For example, you can write it as 1,69 times 10 to the 2 times 10 to the 3 watts, which is 1,69 times 10 squared. The 10 to the 3 watts is like the kilowatts. So you can say also the power is 1,69 times 10 squared kilowatts. And this is the answer. It's the answer. Instantaneous power. Right, so where's a question on this and who actually has a suggestion and has a different opinion to this? Okay, you must learn these things. You must learn these things because if you are to become a mathematician, a scientist, you need to be sharp when it comes to these things. Right, the next question is on the arresters. There are things we call the arrestor beds. Arrestor beds are constructed as a safety measure to allow trucks to come to rest when their brakes fail whilst going downhill. Write down 2 design features of such arrestor beds. These arrestor beds are very, very important, but many times the trucks have a big problem because sometimes the brakes fail off the truck. So if the brakes fail, what happens? What happens if the brakes of the truck fail? So the examiner is saying, write down 2 design features of such arrestor birds. What are the design features? How should these arrestor birds be? Because you can see them when you're driving there. Right, so we note that first point, surface must provide sufficient friction. Like sand. Point 2. Must be long enough. Right, must be long enough for the vehicle to stop. For the vehicle to stop. Okay. Must be long enough for the vehicle to stop. So these are the design features because these arrestor birds, you see them when you're traveling there at the toll gates and many other places where you might have the failure of brakes, of the braking systems. So, and when the brakes fail and this truck can't stop on its own, the surface must provide sufficient friction like sand, and also must be long enough for the vehicle to stop. Right, must be long enough for the vehicle to stop. So yeah, just note that, long enough for the vehicle to stop. So because if it's not long enough, then the truck is going to finish the arrestor bird and still continue accelerating and causing more damage, accidents, killing people, killing the drivers in the process. But if the arrestor bird is long enough, then it's going to provide the stoppage. Okay, that is required. All right, next question. I want to spend some time a little bit. Okay, we look at a question like this, but I feel that we have a little bit of a responsibility to revise it as we have done this particular question that is similar to this. So we need to spend a little bit of time on this. Even tomorrow, I'm planning that we do more. I hope you guys will make the time. And I'm going to give a structured timetable that is going to help us cope with these things, because we need to go deeper into science like never before. But now in this question, learners conduct an experiment to determine how the initial kinetic energy given to a trolley affects the distance the trolley travels. I know I looked at this question before, but I want to look at it in a bit more detail, but also I'm trying to make sure that people sort of understand it. Right. So yeah, how the initial kinetic energy given to a trolley affects the distance the trolley moves on a rough horizontal surface. This is in the same class of questions. So please take note of this and interpret. A learner pushes a trolley of unknown until it reaches point A with kinetic energy, EKA. The horizontal distance traveled by the trolley before it comes to rest is then measured when see the diagram below. Here is the trolley travels the distance delta x, and obviously this is in the same class of questions as the track we just discussed. Okay, right. So now the experiment is repeated with the trolley moving on the same horizontal surface but with different initial kinetic energies at point A. The results obtained are shown in the graph. Right, so ignore the rotational effects of the wheels of the trolley. Okay, we understand therefore that these wheels of the trolley are rotating, and that is why this particular trolley is able to move. But the examiner is saying, please ignore all that and pay specific attention to the kinds of things that they want us to answer. Okay, what does the examiner want us to look at here? They want us to say, ignore the rotational effects here. Draw a labeled free body diagram showing all forces acting on the trolley during its motion after passing point A. Right. So now let us look at this question and draw, right, a free body diagram. Now, the question is, how does the free body diagram look like for this particular kind of motion? So we interpret this and draw the free body diagram very, very carefully. Now, this then pushes the trolley of iron mass and reaches the point A with kinetic energy EKA. Right, the horizontal distance traveled before it comes to rest is measured there. Now, there are a couple of things that are very important. There is a rough horizontal surface, meaning therefore there is friction. The free body diagram therefore is going to be such that this trolley is going to have a weight. This is going to have a normal force. This is going to have friction. Because the surface is rough. So the answer to that, to draw a free body diagram showing all the forces acting on the trolley during its motion after passing point A, this is the situation. So you're going to have that the surface is exert a force on the trolley called the normal force, exerted on the trolley by the surface. But moreover, you'd have the couple of other things that are very important, like your weight and also the friction, because the surface is rough. Remember that by the time it reaches, the experiment is repeated, the trolley moving on the same horizontal surface, but with different initial kinetic energy, kinetic energies at point A. So you have different kinetic energies, and then this trolley moves by itself. Right. So this learner pushes the trolley. A learner pushes a trolley of unknown mass until it reaches point A. With the kinetic energy EKA, the horizontal distance traveled by the trolley before it comes to rest is then measured. See the diagram below. So you have this kind of a situation, okay? And we have drawn the free body diagram, and this is it, and it is very enough. Next point. Ignore the rotational effects of the wheels of the trolley. Name the independent variable that in this experiment. The independent variable is what these guys are changing, and also what are these guys changing here? This guy, the experiment is repeated with the rod moving on the same horizontal surface, but with different kinetic energies, different initial kinetic energies. So your initial kinetic energy, initial kinetic energy. Okay, the initial kinetic energy is what these guys were changing, or you can say it is EKA. These guys were giving it more push, but also they could give this trolley less push. So in any of these instances, you can see that if you push it a lot and it moves faster, by the time it reaches A is faster, then it's gonna reach this point there. But it could potentially be slow as well. Okay, so we continue. We continue. Ignore the rotational effects of the wheels of the trolley. State the work energy theorem in words. Okay, I know that everybody knows that one, but I'm going to state it. And we say that the net work done, right? The net work done on an object. The net work done on an object is equal to the change in the object, object's kinetic, energy. The net work done on an object is equal to the change in the object's what? Kinetic energy. And this is called the work energy theorem. Right. The net work done on an object is equal to the change in the object's kinetic energy, and this is work energy theorem works. Right, so now ignoring the rotational effects of the wheels of the trolley, calculate the mass of the trolley if the coefficient of kinetic friction between the wheels of the trolley and the rough horizontal surface is 0.18. Now let's just look at 5.4. Now I want us to look at these very carefully. So we want to calculate the mass of the trolley. And to find the mass of the trolley, we look at the fact that this is the formula we use. The force of kinetic friction is mu k Fn. Mu k times the normal force. And this is the formula we use here. Because we know, therefore, that the force of kinetic friction is given by the coefficient of kinetic friction times the mg. Right. And obviously, we need to calculate the mass of the trolley if the coefficient of kinetic friction between the wheels and that. So this is mu k, that is mu k is 0.18. Right, so with this stated, but now we need to note that we need something there to calculate this. And what do we need? We need to know that we need to be able to find the gradient. Right, the gradient is delta y, delta x, this gradient. What is the gradient? Good. The gradient. Now we come and want to find the gradient. The gradient is change in y, change in x as we know it. But at this point, the gradient is going to be the change in x because it is the change in the vertical axis, change in y. So it's delta x, and which is also divided by the initial kinetic energy. So you can say it is delta x ai. So Okay, so you have the gradient, which is delta y, delta x. Okay, from mathematics, the gradient is delta y, delta x, but we can see there is change in x divided by EK, EKI. Right, so, and obviously that would be the EK initial, because they were changing the initial velocity there. And as they were changing the initial velocity, but this here can be seen as what? Right, so, and it is nothing other than therefore 1 over the friction, kinetic friction. And therefore, if you look at this now, you can pick a couple of values. But now, if you look at the fact that it's going to be the change in, you can take 1.5, the delta x here is the difference between 1.5 and 0, 1.5 and 0, and you get 1.5 and divide by the change here, which is 6 minus 0, which is 6. So you can take 1.5 over 6, basically. Right, something like that. So you come here, and then you want to find the gradient. So which means that the gradient would be 1 over f. Right, so that in the end, so that you have 6 divided by 1.5, which is 4 newtons. 4 newtons. Right, so obviously this one becomes the force of kinetic friction. And then you take the force of kinetic friction, you bring it here. And if you bring it here, then what you're going to have is that this is going to be exactly 4. The mu is, mu k is 0.18. 0.18 times the mass is what we want, and therefore 9.8 is the gravitational acceleration. So which is 4 divided by 0.18, 9.8, like this. Okay, if you divide these things, you get 2.27 kilograms. And this is actually the required mass. This is the required mass of the trolley. Okay, who has a question here, as a matter of fact? Who has a question here? Right, so that is something you need to realize in this question and take note of. And obviously, we continue to analyze more questions as we move forward. Right, moving forward, I want us to spend some time on the ambulance. Right, I want us to spend some time on the ambulance question. An ambulance is moving. Okay, this is called the Doppler effect. Right, this section constitutes what you call Doppler effect. An ambulance is moving away from a stationary listener with a constant velocity of 25 meters per second. The siren of the ambulance emits sound waves, a frequency of 550 hertz. The listener detects the frequency of these sound waves to be 512.64. Right, Melody, yeah, I'm finishing my class now. My brother, please just give me like 15 minutes. Yeah, I'm finishing it now. Just that I'm finishing my class. I'm in class now. I'm having an online class finishing in about 15 minutes. That's fine. That's fine. We've already done much of the work. That one I'll just submit quickly because it's done already. All right. Thanks, my brother. Thanks. Goodbye, my brother. Right. So now the siren of the ambulance. Yeah. The siren of the ambulance emits sound waves at a frequency of 550 hertz. The listener detects the frequency of these sound waves to be 512.64 hertz. Ignore the effect of wind. State the Doppler effect in words. Now let us look at these, but look at these very carefully. What does Doppler effect mean? Let us state this Doppler effect in what? In words. And this is the statement. We say for Doppler effect, we say the change in frequency. The change in frequency of sound waves, or a change in, frequency, or the change in pitch.
Okay, that's a 9.
Of the sound waves.
9 plus
8. Of the sound waves.
19 times 2.
Right. Or of the sound. The change in frequency of the sound detected. Right. Detected by a listener.
Yes.
Right. By a listener. Because the sound. Because the sound source and the listener have different
9 times 2.
Have different velocities. Have different velocities. Relative. Right, to the medium. Relative to the medium of sound propagation. Of sound propagation.
4.
Right, so the change in frequency, pitch of sound detected by a listener. Right, because the sound source and the listener have different velocities relative to the medium of sound propagation. Okay, this is the story. And this is Doppler effect in words. So take note of these and make sure you understand this Doppler effect. Words. So let us solve some problems on Doppler effect. The next question. Ignore the effect of wind. Use the information, the given information to calculate the speed of sound in air. The speed of sound in air. Let us find the speed of sound in air together. Right, so we're able to recognize that for the formula we're going to use is that the frequency of the listener, velocity, plus or minus the velocity of the listener divided by velocity plus or minus velocity of the source, frequency of the source. And therefore at this point, this would mean that an ambulance is moving away from a stationary listener with a constant velocity of 25. So now there is data that we can write down here. So we are noting the velocity is moving away from a listener with a velocity of this. So we have the velocity of the source. Velocity of the source of the ambulance is 25 meters per second. The siren of the ambulance emits sound waves at a frequency of 550. Right, so the frequency of the source is 550 hertz. Right, the siren of the ambulance emits sound waves at a frequency of this. So you have the frequency of the source, which is 550 hertz. the listener detects the frequency of these waves to be this. So you have the frequency detected by the listener, which is actually 512,64 hertz. What is the velocity of the sound in air? Okay, so that you put velocity 512, the frequency detected by the listener, frequency detected by the listener is 512,64, which equals, okay, yeah, that's fine. And then you have the velocity, and you'd have also the velocity of the listener. Right, remember that the ambulance is moving away from a stationary listener, so that the velocity of the listener is 0 meters per second. Right, so you have 0 here. You have V. The velocity of the source is actually 25 here. 25 meters per second. Let's bring it out for simplicity. Right, so that in the end, then you have the frequency of the source, which is 550. 550 hertz. Good. Okay. 512. 550 V V plus 25. You cross multiply these things. Cross multiply these things. 512,64 plus 512. Okay, yeah. Okay. Right. Okay, plus 512,64. You cross multiply these things. So it's 512,64 times V. So it's 512,64 V. And the 512,64 times 25. So it's 512,64 V plus 512,64 which is 550 V. Okay, like this. And then you just solve. Right, this is a V. And then now we just manipulate algebraically. 512,6425 equals 550 V 512,64 V. Okay, let's use our calculator to finish this off. So if you have 512,64 25. Okay. Yeah. Okay. 550. 550 V. 512,64. Okay, so we use a calculator to simplify these things. So if you use a calculator to simplify these things, you are able to get that the 550, just 550 minus 12. You can do that quickly. 550 minus 512.64, which is 37. 37.36 V. You can put a decimal comma, which is 512.64 times 25. 128. 128.16. 128.16 divided by 37.36. 128.16. 37.36. Okay. Sorry, I lost numbers there. 37.36. So we're getting exactly 343, 0.04068. Okay, good. And then this one is approximately 343.04 meters per second. So yeah, that is the answer that we have here. Okay, I have two people waiting outside here. Okay, I did all. I'm sorry that you found yourself having to wait, and this thing is blocking you out sometimes. You'll forgive. I think it's just network issues. It does happen. But in the end, then we're able to find that we to calculate the speed of sound in air, and therefore the speed of sound in air is exactly this one. Obviously, we know the speed of sound in air is 343.404. Yeah, we to calculate it because, but yeah, it's given at the back of the metric paper. So it's something that you really can be aware of. Okay, so we continue. Let's look at the next thing. Right, we continue to try the next question. Okay, we have already read the story above, but we just need to continue. Ignore the effects of wind. If the ambulance moves away from the stationary listener with a constant velocity, which is greater than 25, how will each of the following change? Choose from increases, decreases, or remains the same there. So we continue to answer this question. So if the ambulance moves away from the stationary listener, remember that ambulance in this part of the question, you're talking an ambulance is moving away, right? Because the ambulance was moving away, we were able to realize that if the ambulance is moving away, we had a plus sign here. Take note of we had a plus sign there, signified that it's moving away. Because if it's moving towards, then this is going to become a negative. Okay, take note of that. If the ambulance moves away from the stationary listener with a constant velocity which is greater than 25, okay? If the ambulance is moving away from the stationary listener with a constant velocity which is greater than 25, because here it's moving away from a stationary listener with a constant velocity of this was constant. But now, if it is a constant velocity which is greater than 25, right? So now the question is, how will each of the following change? Choose from increases, decreases, or remains the same. The speed of sound in air. The speed of sound in air. Right, so what will the speed of sound in air be? The speed of sound in air is constant, and therefore it remains the same. And therefore it remains the same. Remains the same. The frequency of the sound waves emitted by the siren. The frequency of the sound waves emitted by the siren. Right, remember that the frequency of the sound waves emitted by the siren do not change, so they remain the same because it's just a speed. So the frequency also remains the same, which is the frequency of the sound waves emitted by the siren remains the same. Right, because it is the same siren. It is the same siren. Just the speed now, what we're told here is that the ambulance moves away from the stationary listener with a constant velocity which is greater than 25. Okay. The frequency of sound waves detected by the listener. Right, because it's moving at twice the speed, then the frequency of sound waves detected by the listener decreases. Why is there a decrease? Because now the ambulance is moving faster away from the listener. It's moving fast away from it. Therefore, the frequency of the sound waves detected by the listener decreases. Now, in the next question, we're looking at the spectrum of a distant star. The idea of a spectrum of a distant star, when viewed from the Earth, is redshifted. What does redshifted mean? It's a star moving away or towards the Earth. If the star is redshifted, then it is moved away from. So the answer here would be away from. Why? Because you can see that if the star is redshifted, so if you see a red star in physics, it means that in science, it means that the star is moving away from. It's like a car. A car, if you see a car and you see the red lights of a car, if the lights of a car are red, you know the car is moving away from you. Because if the car is driving towards you, then you're gonna see the headlights, and the headlights are not red. If you are seeing red lights, you know you are seeing the back of the car. If you are seeing the back of the car is moving away from you. So this is the same as the spectrum. The spectrum of distant star viewed from the Earth is redshifted, moving is moving away from. 6.2.2. Use the Doppler effect to explain the answer to 6.2.1. 2 marks. Okay, let's use the Doppler effect to explain these. Right. A lower frequency. A lower frequency, or what we call a longer wavelength. A longer wavelength is detected. The spectral lines are shifted to the red end. To the red end of the spectrum. Okay. A lower frequency or longer wavelength is detected. The fact that is red shifted, it means that there's a lower frequency or a longer wavelength, because the red light has lower frequency or longer wavelength. So the red shiftedness means that you have a red light, and red light means you have lower frequency or longer wavelength is detected. The spectral lines are what? Are shifted to the red end of the spectrum. If the spectral lines are shifted to the red end of the spectrum, what does it mean? It actually therefore means, therefore, this spectral, okay, the spectral, let me just write that, spell that correctly. So the spectral The spectral lines are shifted to the red end of the red end of the spectrum. Right, so the spectral lines are shifted to the red end of the spectrum. You see, if they're shifted the red end of the spectrum, yeah, the lower frequency or longer wavelength is what is detected. All right. The spectral lines are shifted to the red end of the spectrum because it's red shifted. So the spectral lines are shifted to the red end of the spectrum, but red is associated with lower frequency and longer wavelength. All right. Yeah, I'm not going to be long today. But now I'm going to communicate to you again to meet and do science. So we shall meet again and do more science. Tomorrow is a holiday. How many people are going to school tomorrow? The first of May.